Okay, back to chapter 3. We are going back into heat treatment. It started talking about changing the temperature above where, or increasing the temperature to where you change the structure of the steel. So I felt it important that we stop where we were. I want to show you this. This is called an iron-carbon phase diagram. Okay, this is going to explain certain parts of, it's in your book as well, there is one of these, it's not on the PowerPoint. It's going to explain at what temperature does steel change structure, and so forth. Okay, I'm going to walk through this with you. So real quick, this bottom scale is the percent of carbon. Okay, the top scale is your side scale here is your temperature. So when I talk about percentage of carbon, here's 6% of carbon. Most steels fall in place here between the 0.08% and the 0. So in this case, it's perlite. Perlite is 0.8% carbon. A good example of this is a railroad track. Okay, a railroad track is perlite. It's right here. It's on the lowest point of the iron-carbon phase diagram, at which temperature range we go from ferritic to austenitic. And this is where your grain structure starts to change at this temperature. So real quick, everything up to this point is still in its original structure that you started with, okay? So this is called our lower transformation temperature. Okay, it's our A1 line. The exact temperature for it is 1,333 degrees. I would bullet that, write it down, and make sure you know that. What is the lower temperature transformation? 1,333 degrees Fahrenheit. Okay? When we go above our lower transformation temperature, this is when the grain structure starts to really change, okay? So at this point, we go from a body-centered cubic structure to a face-centered cubic structure. We're going to talk about that and break that down here in a minute as well, okay? The important thing to know, I want to show you this, is as our temperature rises, so our melting point of steel, it's way up here at 2,800 degrees already. We know we're welding roughly 6,000 degrees. So we're up at the very, very top, okay? I don't even know if you can see me. Probably not. So we're up here at the very top when we are heating the material, okay? When we're welding the material. As we get above 1,300 degrees, our structure changes. And if we dunk it or cool it off, then we change the grain structure, we quench it, we can freeze it from, we took it from a body-centered cubic to a face-centered cubic, and then we quenched it at that point so it's stuck in that position. Okay, we're going to break that down here in a minute. But that's what happens when we're talking about heat treating, adding strength, quenching things, and so forth, is that we've taken it to this point. Beyond that, we're heating it, and then we talk about heat treatment. What we want to do is we want to bring it back up to right here below the lower transformation temperature, usually 1,200 degrees. We're going to let it sit there for a certain amount of time, depending on thickness of material, and we're going to slowly bring it back down. So what we're doing is we're going to soften it, okay? We're going to help soften the material, gain some ductility, but still have added strength because we changed the grain structure. All right? You can read through this some more as we're going along. I just wanted to show you that, and that will hopefully be able to look at that in your book, and we can move forward with this. Okay? Okay, so we talked about that critical point is a point at which carbon changes the structure of steel. So right here, we know, and I would write, or wherever, says your lower transformation temperature, 1333 degrees. That's when we go from ferritic to an austenitic steel, or austenite. It's also in austenites where it is non-magnetic, okay, until we cool it back down and bring it below that. It produces hardness superior to that of steel before heating and cooling. Only medium, high, and very high carbon steel can be treated. I have seen low carbon steel have great qualities added to it. So for example, I've done one with just plain steel, A36 steel. We heated it back up to 2,000 degrees roughly, and we dunked it. We did several different batches, same material. We dunked one in water, one in oil, and then we dunked one in a cold saltwater brine, okay? And they were all out of the same piece of steel, same material, and when we pulled them apart to do a tensile test upon them, there was roughly between 35 to 40,000 pounds difference, and that was even out of mild carbon steel. So again, my mind, a lot of times I'm a prove it type of person. If I have the equipment to do so, I will try to test it just to see what I can get. All right? So we're going to go through this. Let's talk about case hardening real quick. Case hardening is a process that gives steel hard, wear-resistant surface while leaving interior soft and tough. So right here, that sounds almost exactly what we were talking about with the cementation process of adding carbon earlier, correct? Exactly. It's the same thing. If we make the exterior, the edge, or the surface hard, and it doesn't have to be done just by carbon, these are other ways of doing it, then that's what's happening is we're leaving the edge harder, stronger, but the interior still maintains its soft ductility and so forth, okay? These are the different methods that you can do: cyaniding, carburizing, nitriding, flame hardening, hard surfacing by welding, or you can even do a metal spray application upon it now. Plain carbon steels and alloy steels are often case hardened. We're going to break down each individual process, okay? So cyaniding, method of surface hardening low carbon steels. Carbon and nitrogen are absorbed in outer layer of steel to the depth of 0.003 to 0.20 of an inch. It's done in a liquid or a gas form for hard but very thin surface over steel. It's usually done in a vacuum chamber as well, okay? Carburizing. This is a process where low carbon steel is made to absorb carbon in its outer surface. Like we talked about the cementation process earlier. There's a time that it's held with the heat so that it absorbs the carbon within the material. Okay? You have to get to a specific temperature in order to do so. Carburizing compound, again, it depends on what you're using within the carburizing or the carbon. You can use solids, cyaniding liquids, or hydrocarbon gases to do so as well. Nitriding. This was really interesting. I never had thought about this until I started going through like my CWI stuff. With a group that's only used with a certain group of low alloy steels, contains elements such as vanadium, chromium, or aluminum. And what happens is it'll combine with nitrogen to form nitrides. So the nitrogen is not injected, but it's absorbed into the surface, and it does the same thing. It actually creates a much harder case hardening surface. One of the places you can look at this now is a cryogenically treated knife blades for hunting, fishing applications. Even I believe even some kitchen knives are that way nowadays. So parts are heated in nitrogen atmosphere to this temperature, then quenching. unnecessary with little distortion or warpage. Okay. They could be quenched in a liquid nitrogen bath for some of the knife blades that I've seen, or they've been held at a low temperature to help absorb it as well. There's modern advances in technology that's making this much more easily acceptable. Flame hardening. This is the most common one that we see. And what happens is you're just going to take and you'll heat it with a flame on the outside of the surface, run it back and forth. So for example, most of just a surface section of like AR 400, 500 plate to where it's flame hardened. That one is flame hardened throughout the entire thing, but what we're meaning is that it heats it up with the flame, and then we quench it in some sort of a medium or a bath to get the much higher strength or properties that we want out of it, either whether it be strength or impact resistance or abrasion resistance as well. Okay? Annealing. Annealing is, let's go to it. I want to read it out of the book. Page 74, left-hand column, bottom. It says, annealing includes several different treatments. The effects of annealing are to remove stress, to induce softness for better machining properties, to alter ductility, toughness, or electrical, magnetic, or other physical properties, and to refine the crystalline structure to produce a definite microstructure. Reading out of the book, the changes that take place in a metal depend on the annealing temperature, the rate of cooling, and the carbon content. When it's desired to produce maximum softness and grain refinement in previously hardened steel, the steel is heated slightly above the critical range, or the lower transformation range, and cooled slowly. The metal is allowed to cool either in the furnace, which is gradually cooled, or it is buried in lime or some other insulating material. Another form of annealing is stress relief annealing. It is usually applied only to low carbon steels. The purpose here is to relieve the stress caused by working of the steel, such as in welding. The material is heated to a point just below the critical range and allowed to cool normally. So there's two different things we can do with annealing, okay? We can heat it above the critical temperature. If we heat it above the lower transformation temperature, what we're doing is we're starting to rechange to refine the crystalline structure, and we're going to cool it down nice and slow. Now if we don't want to change the structure of it, and we just want to stress relieve it. So stress relieving, anything, especially a large piece of weld that has undergone a large amount of welding, even thin material. Same thing, it can be even thin material as well. Okay, I shouldn't say just large. But anytime we weld, we confine stresses into it. Weld pools contract, stress, and it'll start to pull. Even if you don't notice it, it will create an internal stress, kind of a tension within the weld. So if it's something that we want to, so at that point it also becomes very brittle right along the weld zone, okay? That if it were to pull apart, a lot of times it can be right at the weld zone because of the internal stresses within it. If we want to relieve that stress, we would do a stress relief annealing. So we take it up to about usually 11 to 1200 degrees, most procedures that I've seen done. You'll hold it there for an hour, and then cool it down 100 degrees per hour for every inch of thickness after that. So it may take 4 or 5 hours to bring it back down. Now sometimes you don't have that option in the field. So what you can do is you can heat it up, or you might be able to wrap some electric fans out of it. And then once it gets to that certain temperature, you want to wrap it up with like some insulation, some KO wool, vermiculite, dump in a thing of vermiculite to where it'll cool down nice and slow, and it maintains that heat. It'll slowly cool down instead of cooling down very fast and normalizing, okay? All right. Again, we can break that down much further as we go along later. Differences between Hardening and softening of steels. The faster the cooling rate, due to the rate of cooling, the faster the cooling, it hardens it, the slower the cooling, it softens it. Both tempering and annealing reduce hardness of the material. So tempering. You can highlight that whole paragraph underneath there. There's a few things in there that might, that a question might come out of this paragraph as well. Processes wherein hardness of steel reduced after heat treatment and relieves stress. Okay. You heat the hardened steel to a predetermined temperature between room temperature and the critical temperature. Hold temperature for a length of time. You do the cooling in air or in water. So if we do it in water, it's called quenching. If we let it cool in air, it's called normalizing. So normal conditions, let it cooling off slowly. So if you notice, the main difference between annealing and tempering is the fact that tempering is typically below the critical temperature. Annealing is usually above, so you're wanting to refine or change the grain structure a little bit. Tempering is more like the stress relief annealing that we talked about, and we slowly brought it down. We didn't go above the transformation to change the grain structure. We're bringing it down nice and slow, or you can quench it as well. Usually, when you're tempering, it is going to be just letting it cool back down in air. Okay? Here's normalizing. Improves the grain structure of metal and returns it to normal by removing stresses. Again, you're going to heat it up. It requires a faster rate of cooling than used for annealing. So this is in normal air conditions outside. You don't keep electric heat blanket on it or anything else. You heat it up to 1200 degrees, you walk away and you let it come down to room temperature at normal conditions. Okay? Annealing, you're putting it in a furnace, heating it above. Tempering, you're warming it up below, letting it cool off. Normalizing, you heat it up and you just walk away. So, here's a few definitions that are things to know. Okay, metallurgy. Metallurgy is the science that deals with the internal structure of metals. And if I was you, I would find between your book and this PowerPoint, and I would highlight anything in your book that's on the PowerPoint. There are 4 states of matter: solids, liquids, gases, and plasma. Okay? We can get into the entire atomic particles, electrons, protons, so forth. Atoms are in a constant state of vibration. Okay, let's talk about this real quick, and then we'll go to, Atoms are in a constant state of vibration. Heat energy increases, the atomic movement increases as well. Okay? So, same thing. If it gets hot, I like to compare it to, for example, if you're within a box or within a boundary, the warmer you get, you have a natural home position, you're going to be in the box, but you're going to move around a lot more, you're a lot more active. If it's really cold, there's going to be less movement, so forth. Okay? So the temperature rises, the atomic structure expands. We know that. Material grows as the temperature rises. If it rises high enough, atoms move freely and solid becomes a liquid. They continue to rise. At that point, then there's a vaporizing point. It goes from a liquid to a gas. Superheated, it ionizes, it becomes a plasma. That's a gas that has become an electrical conductor. So here's kind of the four stages of it: solid, liquid, gas, plasma. Okay? Solid metals take on a three-dimensional crystalline structure. Atoms align themselves into ordinary layers. These 4 terms right here, specifically these 3 will be the most that you'll deal with, but it's good to know all 4 of them. Should be closed package, not closed paste. Closed pack. Okay. So, body-centered cubic, face-centered cubic, body-centered tetragonal, hexagonal close pack. These are on page 76, table 3-1. You can refer to them as well. So this is your normal steel, everyday steel. Right here is your body-centered cubic structure. Okay. Iron, carbon steel, chromium, molybdenum, tungsten. Okay. What happens, look at the amount of atoms here. You have 2, 4, 6, 8, 9. You have 9 atoms within there. Alright? Face-centered cubic, now it becomes like a dice. So instead of the one dead center, you now have picked up 1, 2, 3, 4, 5, and 6 on top of your 8. So now you've went from 9 to 14 atoms. So this can happen with any material whatsoever. This can happen even in just plain iron. Even though it doesn't say iron here, this can happen with iron. The difference between these two can be on that iron-carbon phase diagram. So this is below 1300 degrees. Once we get above 1333 degrees, we now pick up 5 atoms due to movement, and we can have a face-centered. If we were to quench it at this point, it could stay in a face-centered cubic crystalline structure. Okay? These are the grades of material that naturally have a face-centered crystalline structure as it is. Same here. Body-centered tetragonal is a martensite. So now martensite, what's that? Martensite is basically, one way that we can come up with martensite is if we take this body-centered cubic, we heat it up, and then we dunk it and quench it. It comes back to an elongated martensite. Remember, we had a lot of movement of atoms, and we froze it there all at once, and now that is our piece of material there. We're going to show some better examples to help explain this better. So right here, that becomes really, really confusing, correct? I agree. Let's back it up. So first thing we have is we have a piece of iron, perlite. So perlite was that railroad track, okay? So it's a body-centered cubic structure, iron carbide, iron, carbon. So these are the layers of cementite within it. You heat it up above that iron carbon, above the iron carbon phase diagram. Okay, it's above that lower transformation. Now it's austenite. All of a sudden it becomes a face-centered cubic. It's got 14 atoms instead of 9. Okay? Here was our base one. Now we have face-centered cubic, 14 atoms. At this point it is non-magnetic. Okay? Above the lower transformation temperature. If you bring it down nice and slow, you cool it slowly, it comes back to a body-centered cubic and to a perlite. Exactly what it was here. If you cool it very fast, it turns into what we call bainite. Okay? Bainite is harder, stronger, but it's less ductile. You cool it faster. If you notice right here, what's the difference? We picked up more carbon. Okay? 2 more atoms of carbon. So we're ferrite, now we're carbon. We've lost iron, we've picked up carbon.